Okay, okay. All right, hello everyone. Welcome. There will be a quiz available tomorrow. Please complete it Tuesday if you can. It is due Wednesday though. Um, Before starting the quiz, I would suggest looking at the solutions to all previous homeworks that are posted. Um, there's one final response due Wednesday, a last homework due on Thursday. Prior to the final, I forget the date. I will get this out in an email or a Canvas announcement or something. There is a math as a process exam inventory thing again before the final. And then what I'd like to do is have the usual office hours this week, Monday through Thursday. Then starting Saturday, May 9th, I'll have a daily morning and afternoon office hour. 9 a.m. to 10:30 a.m. and then 1:30 p.m. to 3 p.m. and also by appointment. So if you need to meet outside of those times, that's why it's not a whole lot of time each day. And also, I can only probably stay anchored so long next to the computer. But yeah, you could always send an email and we can find a different time to meet up. And then for the final exam itself, the take-home final, normally we would have had an exam in class on May 15th. So it'll be available to you the 15th, 16th, 17th, 18th. I hope that's a sufficient amount of time. I would have loved to make it due the 19th, but like I need a grade by the I was looking up when final grades are due, and so I need to get things kind of in order and all that stuff. So today we're going to take a look at combinatorial proof. The overall goal of combinatorial proof is to prove that an equation is true, that an equation is true, but in a rather unique way. What have we done all semester when we need to prove an equation? Like even way back to an even plus an even is even, we've started with one side of the equation and then substituted based on things we already knew. This is going to be a totally different approach to proving an equation is true. First of all, just to make sure we're clear with what I mean by counting problem, I'm not going to define it per se. I'm just going to give an example of a counting problem. In fact, one that's a good review of what we did last Thursday, last Wednesday. Excuse me. How many? Oh, there's a y'all. My goodness. Turn in an exam today, right? Is that correct? Oh my goodness. Sorry, I'm like almost done grading calculus exams. I had them due earlier, so turn in exam today. Is that correct? I, my goodness. Yeah. Um, so look, what's a counting problem? For instance, how many ways are there to give n pieces of candy to 10 people? So this was the type of counting problem we looked at last. I was saying Thursday, and that reminded me. Oh wait, Thursday was exam day, right? So, yeah, turn in an exam by today. But so we asked a question like this on Wednesday, and I won't right now, because we've got other things to do, go review Wednesday's class. There's some discussion about this, but the point is, this turns into accounting via bijections thing, where you have n candy symbols. I think we used C's, capital C's as a candy symbols last time, and then 9 vertical bars as dividers. For 10 people, you only need 9 divider symbols. And so then that, some further discussion led to n plus 9 choose, n plus 9 choose 9. Again, there's more things I certainly want to say about that, but I'm just like, here's an example of a counting problem and a brief summary of its answer. Today, what we're going to do is talk about combinatorial proof. And the question that gets asked is really different. Okay, the question that gets asked is something like this: prove that, and then this equation equals that equation. Now I'm going to intentionally hatch these different directions. So I'm going to do my shade that way, and then shade this diagonal this way. Okay, I could, I guess, use color, but so you have an equation, you have a left side, and you have a right side. Here's what you do. This is really different. How do you answer a question like this using the method of combinatorial proof? 3 steps. Step 1, you come up with a counting problem. Maybe I'll just clarify, you come up with a counting problem question. So, for instance, up here, right, like there's this, how many ways are there to give n pieces of candy to 10 people? That's a counting question. So you have to come up with a relevant counting question in step 1. Step 2, you answer your counting question. Right? So in step 1, you ask this question. Step 2, you answer your own question, obtaining what was the left side of the equation. So I'll shade that this way. Okay. Well, but like obviously using valid counting techniques. I mean, not just made up stuff. So using valid counting techniques. And then step 3 is to answer your counting question again. Answer your counting question, obtaining now the right side of this equation up here. So let me shade this the other direction, this way. So obtain that one, right? This one's this one. Using, again, of course, using valid counting techniques. Your reasoning must be correct, not just made up things. Using valid counting techniques. So if you answer the same question 2 different ways, but both of the ways of thinking about them are correct, then it should be that these 2 things up here should be equal. So I'm going to summarize this by saying what happens here is you identify something to count. Then count that thing that you'd identified 2 different ways, and I put different in quotes. Sometimes I think people get real confused by this word different. What I mean by different ways is you use one thought process to answer this counting question, that thing that you identified needing to be counted, and then you use a different thought process, still a valid thought process, to count again. So I want to really clarify this by doing the following little thought experiment. Because I think people get real tripped up by what, like, this is actually, I mean, look, when we actually look at a specific question and going through the process of coming up with your own question, that can be challenging. But like the principle behind what's going on here, I don't want it to be some magic. So I want you to think about the following separate situation, right? So suppose I give you a counting problem on a quiz. I give you a counting problem. The timing of our quizzes is we won't actually ever have that happen. That would have been a quiz next Tuesday, but that's not happening. So let's just say on the final or something, right? So I give you a counting question, and then it's on a quiz or on a test, and so one student, so student number one, answers correctly. So using correct methods, product rule, sum rule, binomial coefficients, whatever, like validly thinks about it and comes up with an answer. And I read the work from student one and go, yeah, that's good reasoning, should earn full credit. And student two answers correctly, uses the product rule or the sum rule or whatever applies, and I'm looking at the reasoning, and it's like, yep, that's correct reasoning. That works. That answers the question. However, the final answer for both students looks different. Then what should be the conclusion here? Right? So I ask a counting question on an exam, and student one answers the question correctly, student two answers the question correctly, but the two students have different looking answers. Then the conclusion really ought to be that what one student answered and what the other student answered are equal, right? So this might be student one's answer. And this would be student two's answer. We get what's happening here is the big idea, if we step back, is there's a counting question that we think of and then answer the same question with two independent minds. Like, think about it one way and come up with an answer that's valid, and then think about it again. Think about that same original question again. And so in principle, up here, step 2 and step 3, you can swap the order, right? Because you're thinking about the question, and then you're thinking about the question again and answering it again. So shall we look at an example? I think it's time we do that. So theorem for all n in positive integers, the sum j going from 0 to n of n choose j is equal to 2 to the nth. Again, we're going to use the method of combinatorial proof. So 3 steps: come up with a counting problem, and then answer it once, and then answer it a second time. First of all, I'll just mention that we discussed the proof of this when we talked about binomial coefficients and all this. So one way to prove this, you plug in x equals 1 and y equals 1 in the binomial theorem, which I'll just as a reminder include here, was for all n, I'll leave that out right now, but it was sum j equals 0 to n of n choose j times x to the n minus j y to the j equals x plus y quantity to the nth power. So I've swapped the two sides of the binomial theorem from the way we used to present it, but that's one way to provide a proof. It's just this proof is not a combinatorial proof. So we already proved this statement, but we're going to do it a totally different way. We're going to try this combinatorial proof thing. So instead, to prove this, so for all integers n, so let's just let n positive integers be arbitrary. So this is fixed n, and then let capital A be a set of cardinality n. So somebody picks a set of cardinality n, and we'll just call that A. There's n things in the set A. And then the counting question here is to ask how many subsets of A are there? Okay, so then one way to answer this question, okay, is first of all there are n choose 0, if we write that out, n factorial over 0 factorial times n factorial. So 0 factorial over 0. Well, let's see. Let's write it this way. So canceling out the n factorials on top and bottom. So 1 over 0 factorial. This is 1 over 1. There happens to be one subset. I'm just going to use the plural though. Subsets of cardinality 0. So what I'm starting to do here is just set up. I know the counting question says how many subsets of A are there, just without any other restriction. But what I'd like to do is let's just count how many subsets of A have cardinality 0. The cardinality here is referring to the subset. Okay, so the number of subsets of A whose cardinality is 0, that number is 1. Right? We can even write what that one set is in this case. It's the empty set. Now, if we continue this pattern, there are n choose 1 subsets of A whose cardinality is 1. Right? It makes sense we're using this binomial coefficient or this choose thing, right? So out of n things, choose 1. Same deal. There are n choose 2 subsets of cardinality 2. Right? You got to go back and sort out, right? Like, when do we use combination numbers versus permutation numbers? But here, if we're talking about just subsets of A, order doesn't matter. And out of the n things that there are in A, you're choosing 2 of them. It's counting how many subsets of A have cardinality 2. You know, there are, same deal, n choose 3 subsets of A whose cardinality is 3, and so on and so forth, right? We just keep going like this. There are n choose j subsets of cardinality j. So all in all, if you want all of the subsets, now if you pick a single subset of A, just to talk about the process of counting how many subsets there are, you would either pick a subset of cardinality 2 or cardinality 3 or cardinality 4, not both, right? Not each. So the total number of subsets is, the sum rule applies here. You have the sum j of these things. These are n choose j's. It's just, this is the example. This first line is when j is 0. Here's when j is 1. Here's when j is 2. Here's when j is 3. And this last line here that we wrote was just generically. J starts at, okay, so j is really actually representing the cardinality of the subset. So j could be 0 at the smallest or n at the largest for subsets of a set which started with n elements. So this is the total number of subsets. But due to the sum rule, it's the sum j equals 0 to n of n choose j. Okay, so stepping back here, let me box this. This is one answer. It's a somewhat long-winded answer, but it is an answer to this counting question. Right? So instead of looking at all the subsets of A all at once, we're saying let's just look at the subsets of cardinality j for a fixed j. But then we've just kind of looked at that little slice for a moment. We need to look over all possible j values, and j can range between 0 and n. But now what we're going to do is go back and answer this counting question a second time. Well, the number of subsets of a set of cardinality n is 2 to the nth by the work that we did the previous time using this counting using bijections thing. So one answer to this question is this, and the other answer is that. They look totally different, but both ways of reasoning work. So our conclusion is that the sum j equals 0 to n of n choose j, this is equal to 2 to the nth. So this is the combinatorial proof. Come up with a counting question, answer the counting question once, set aside that reasoning, revisit the counting question, answer it again. So let's pause here. Let's take some questions. There's usually questions. Feel free to unmute, ask a question, and clarify something. Maybe I'll zoom out just for a moment. Maybe more of it can be shown on screen at once. How are we doing? Are power sets relevant to this counting question? Well, if we're talking about subsets, then I guess so, right? So the power set of a set is the set of all subsets. And I mean, the way this was worded did not mention the word power set, but Mitch, to answer your question, the counting question could have just been phrased, what is the cardinality of the power set of A? But I think adding that layer of language right now doesn't help with dealing with just really digging into the question. At some point, we got to get our hands dirty and just like actually answer the question. So I didn't want to bring up power set. Like beyond that, power set isn't actually all that relevant here. Can you point out what the two counting questions are you came up with? Yeah, no, I can't. Because, sorry, I didn't mean to be snarky. Because there aren't two counting questions. There's one counting question which was answered two different ways. That's the key thing. Let me go back up. Over here, come up with a counting question, one counting question, then answer it, right? So the one counting question is answered two different ways. There are not two counting questions here. There's one counting question. The counting question is, how many subsets of A are there? Starting with A being a set whose cardinality is n. Here is one answer to that question in this box. It took a lot of time and space to talk about it. Then the other answer to the question was just borrowing the work that we did a previous time, and this second answer is real short, mainly because we already did it, and the time we did it before it was a longer answer that talked about the product from all this business. Is it almost like proving an if and only if? I'm not quite sure. In proving an if and only if, you start assuming one thing and prove another. I don't know. I mean, it depends on exactly what your analogy is, but I guess I don't see it. I think here's the thing. I think some of the questions, like, I appreciate the questions that are coming through, but I think there's too much of this. Is it relevant to power sets? Like, if we're getting a little too philosophical, then I don't think we're actually answering questions that are helpful and germane to the discussion right now. Your first answer to the counting question involved walking through examples to find the pattern. Would you include that in the formal proof? I would probably not include all this text here to answer your question, right? Like, all this talk about like specific subsets of cardinality 0, 1, 2, 3, and even mentioning the specific one, all this text that's circled in blue, I thought I'd just include to help clarify what is meant by this one line down here. It's almost like the argument, I'm glad this is coming up, is the argument for the first way of counting is just really what's in the red box. But if I just started with that, I think it would have been a little unclear. That's all. These are good questions. What else do we have? Yeah, so one counting question. The counting question is answered with two different minds, right? Like, yeah, obviously one of these explanations is shorter than the other to come up with an answer to the question, but it allows you to come up with two answers that look rather different. And these expressions right here are actually, they are literally equal. I mean, that's the thing. That's the whole point of combinatorial proof, is that you come up with a counting question and answer it two vastly different ways, and then you end up seeing an identity. I mean, and I mean identity, like trig identity style, like this is equal to that. Neat questions. What else do we have? Is it time for another example? I'll start another example, but if I see a question pop up, I'll answer it. Theorem. This one's called Pascal's Identity. Let n greater than or equal to k be positive integers. Such that. Oh, no, that's already. Oh my goodness, there's repeats in my notes. Then, binomial coefficient n plus 1 choose k is equal to n choose k minus 1 plus n choose k. So, cool. That's the theorem we're going to prove using this method of combinatorial proof. We can go ahead and start with the let n greater than k be positive integers. Sure. I don't have that in my notes. I'll just do a little better here in class than my notes have. But the thing is, even before looking at my notes, I'm staring at all of this right here and thinking to myself, okay, n plus 1 choose k. Like this is the kind of thing I wanted to encourage you to start thinking about last week already to make it active. Was like, think about what a situation where you'd have binomial coefficients even appear in the first place. So here there's this idea of choosing k things when there's a menu of n plus 1 things to choose from. And then on the other side, there's choosing k minus 1 things versus choosing k things, and starting with n things, there's a plus sign, there's probably there's like a sum rule thing going on. These are already the thoughts that are going through my head in designing hopefully a relevant counting question. And I mean, this is new, so it's this next part looks like it comes out of thin air, but it takes a little getting used to. So I'm gonna just start it and say let capital T be a set of cardinality n plus 1. So if you don't like it to be as boring as just a set of cardinality n plus 1, you could do things like say that n plus 1 people are trying out for a soccer team, or whatever. You can create more of a story to it than just sets if you really like. Okay, so then the left side. Here's the left side. Let me do better than my notes here right now. So the counting question is, how many subsets of T have cardinality K? Right? That's really the counting question, and the left side is a very direct answer to this question. Right? The left side. So answering this question once, the left side counts the number of ways of choosing k things from n plus 1 things. Right? That's what this binomial coefficient is, or this combination number. Right? It's you start with this many things, n plus 1 things, and then you have to pick k of them. How many ways are there to do this? There's n plus 1 choose k. All right, so that's already answering the counting question once, right? That's the direct answer, because the left side's a very direct looking thing, just n plus 1 choose k. The right side's going to be more work, right? Just kind of based on how it's written, it has to be. So here's so now here's the second answer to this counting question. Let me, so here's, right there was answer 1 to the counting question. Right now we're about to start the second answer of the counting question. This one's going to be longer. So I'm going to include the sentence as I have in my notes, not that we have to, but we express this number. I'm talking about n plus 1 choose k in a different way. Now here's the thing. T has cardinality n plus 1, and take a look at the right side. Both binomial coefficients have an n in the upper part, so we got to get from a set whose cardinality is n plus 1 to a set of size n instead somehow, right? So the thought I have is, let's just pick an element of capital T. And I really mean exactly what this sentence is. This is let A in T be arbitrary. So I'm saying that you as the reader whoever's reading this proof, you as a reader, any you get to select one element from T to be A, to be called A. Any element of your choice, but you fix it, right? And then let S be the set T set minus singleton A. See what happened is, well, it doesn't really, it literally doesn't matter which element from T is picked. So just have the reader pick something. And then we've designed the set S where we've intentionally started with T but cut out one element, just cut out the element A. So of course S has one fewer thing. So the cardinality of S is N. This is good because if you look at the right side, there are two binomial coefficients which both have an upper part of N. Now here's the thing, we still need to answer this counting question here of how many subsets of T have cardinality K. So to choose, I'm just starting a new paragraph, but it's still part of this answer here. Still part of this answer. To choose K elements from T, you may either include A, this element little a, by the way, it belongs to T, but not to S, right? So isn't little a in T set minus S? So in T, but not in S. So to choose K elements from T, you can either include this element little a or not. Either this element little a is one of the K elements, or it isn't. And this sounds almost like a proof by cases. I don't want to call what's happening here next a proof by cases, but it has some of the same sort of logical thought process as that. If little a is one of the if little a from capital T is one of the K elements, of the subset that we're making at the moment, then in order to finish making a set of cardinality K, we need to still choose K minus one more things, right? So choose, to complete out our set, we have to choose K minus 1 elements of S. On the other hand, if the A is not one of the K elements, so how do we build a subset of T that has K elements if we did not pick little a as one of those elements? Then we still need to pick all of our remaining elements. So we need to choose K elements of S. So take a look. Either this process occurs or that process occurs, but not both, right? So the total number of ways to do this is, so by the sum rule, the first part here, so A was one of the K elements, but then, so that's already fixed, right? It's just one of the elements. So then out of this set of cardinality N, we need to pick K minus 1 things. So that's N choose K minus 1. But by the sum rule, the other procedure might occur. So if you have an element, if you have that element A, it's not one of the K elements, then to create a K element subset of T, you have to start from your N element set S and choose K of them. So that does it. Right? This is the right side. I know this looks actually a little confusing. If I zoom out, maybe we can fit just a little more on screen. We see the whole thing. The whole point is the left side, the counting for the left side is right over here. And it's just saying start with a set of cardinality n plus 1. And how can you get K of the things in the set? And the number of ways that can occur is n plus 1 choose K. The right side, I'll highlight this in another color. It's down here. The way to think about it now is, let's, out of all of the n plus 1 things that are in T, let's just fix one of them to be called little a. And then to build a subset of T, either you have A in the subset or you don't have A in the subset. If you do have A in the subset, but you need a subset of cardinality K in the end, so if you have A, there's this many ways to complete the set to set of cardinality K. Since you already have A, you're already declaring that A belongs to the subset. There's n choose K minus 1 ways. But if you didn't pick A and you intentionally are saying, now let's only think about the subsets that don't have A, then there's n choose K ways. You see what's going on here? It's the whole point is S is all of T with the exception of one element A. And this is just a matter of, we're counting the subsets of T of cardinality K that have A separately from the subsets of T of cardinality K that don't have A. That's all that's happening. I will pause for questions though, because this it always feels a little more confusing when you kind of, it's a lot easier if you revisit this. But it may be confusing, so let's pause for questions. Again, you've got the set T of cardinality n plus 1. Let's make as many, how many subsets of size K are there? Right? That's what the left side is. That's what's in blue. The argument in red, maybe I should actually also box the argument over here. It's the much longer argument is, okay, so there's still this set T that has cardinality n plus 1. Let's just pick one of those as the special element called lowercase a to follow our notation. And to make subsets of cardinality K, you either include little a or you don't. So if you include little a in the subset of cardinality K, that's just one element. To make a set of cardinality K, and you know one of the elements is a little a, you have to pick K minus 1 more things. But out of a field of only n things, right? So of the remaining n things, you have to pick. Again, then if a is not one of the chosen elements, then out of the n things that are not a, you have to choose K things. Maybe I'm over explaining now, so I'll just takes some getting used to for sure. We answered one counting question 2 different ways, but since one way produced what was circled in blue up here, and one way was answered, and the final answer is what was boxed in red here, those two expressions are actually equal. And they really are. Like you can literally pick n and k to be positive integers where n is greater than or equal to k, and just run this through a computer. Plug in some values of n and k. This actually works, and it should, because we have a proof that this works. But you can just computationally check if you'd like. Can I try another? Let's do another. I just feel like there's got to be another question, but we'll try. The next one in my notes is called Mons Identity. So let m, n, and r be non-negative integers. Such that r is less than or equal to m. Ooh, let's write that a little better. R is less than or equal to m, and r is less than or equal to n. Then, so here's the identity that's going to be true. M plus n, choose r, is equal to sum k equals 0 to r of m choose r minus k times n choose k. Whew. Okay, this one looks real bad, right? But I promise it's not too bad. So sometimes the easier thing is on the left side, sometimes the easier thing is on the right side, right? I mean, if we swap the two sides of this equation, it doesn't mean, so you don't always have to start on the left side, is what I'm trying to say. Look at the equation that you need to prove being true and pick, at least to get started, pick the side that looks easier to deal with. Why not, right? So in this case, m plus n choose r. What's a very natural way? And I'm asking the crowd, I'm looking for someone to unmute or to type into the chat. Like, what's a natural way to think of m plus n choose r? If it helps you out for a moment temporarily, you could just assign little p to be m plus n, and I guess just answer then what's p choose r? Like what's that? What would be a natural way to think of p choose r? We'll wait awkwardly. Choose r things, right? From a set of cardinality m plus n, or from a set of cardinality p. So that's what I want to do, right? Like I actually, let's set that up that way. So we need a set of cardinality m plus n. And what I'm going to do, the m and the n though, you can see are going to be kind of relevant for the other side because there's an m and an n as the upper parts of the binomial coefficients there. So I think in starting the proof, let's actually do this. So I'd like to actually say, how about we let capital A and B be disjoint sets with the cardinality of A equaling, I went with cardinality of A is n and cardinality of B is m. Okay. So then, so the counting question, I'll do better than my notes actually have here. The counting question is how many subsets of A union B have cardinality R. Yeah, that's and the point is then if we look at one way to answer this question, I'll just call it an experiment here just to change up the language a little. Sometimes this helps. Right? The whole point here, if you don't want to answer it so directly like this, it's you dump all the elements of dump all elements of A and all elements of B in a bucket. I mean, what that creates for you, of course, is the set that's the union. And then the whole point is here to answer, this is how many ways are there to choose R things from this bigger bucket. So if you don't want to use boring old set language, you don't have to, right? You can really, if you want, think of this like there's this bucket that has prizes in it. There's n prizes in one bucket. There's m prizes, which are all different from the other ones, in another bucket, and all the prizes are stuck together in some bigger bucket, and somebody won and they get to choose R of the prizes. Right? That's one counting, right? So that produces this n plus n choose R. The second way to answer this question, or the second thought experiment number 2, is to do the following. First, I'm going to say first we pick a number k in 0, 1, ... all the way up to R. Okay, so then what I'd like to, and by the way, we're going to run this experiment here. I mean, I know I'm just saying for a fixed k right now between 0 and R, but we're going to run this experiment for every possible one of these numbers between 0 and R. I just want us to think just for a moment, pretend that k is a fixed number like 2 or something. So then, how do you create a subset of A union B with cardinality R? Well, first pick k elements from A. And remember, we're trying to create a set of cardinality R. So then you have to pick some number of elements from B. Think about it. How many things do we have to pick? If we started by picking k things from A, and we need r things total, k plus fill in the blank here has to be r. It's got to be r minus k, right? Yeah. Oh, thanks. Okay. Sorry, I didn't see it in time. I was just yeah. So k added to r minus k is what's going to equal r, right? So and then let's think about this. The number of ways to do this thing. So if you have to pick k things from A, and let's recall it up here, A has n things in it. The number of ways to do this is n choose k. There's n choose k ways to do this thing, and the second thing, there's B had m things in it, so there's m choose r minus k ways to do this thing. So then, but in order to create a subset of cardinality R, you have to do both of these things, right? Both have to be done. So maybe my notes are a little sparser, but let me say it this way. The number of subsets of A union B with cardinality R, was it R? Yeah, I think it was, yep, R up here. Sorry for the scrolling. With using exactly k things from A is, right? So to now report on that number, since both of these things have to occur, we have to multiply those, right? The product rule applies here. So we'll have n choose k times m choose r minus k. However, so this expression right here, this product of these two binomial coefficients, just expresses how many subsets of appropriate size there are for a fixed k. But the number of things taken from A does not have to be fixed to be whatever we said k was earlier. It doesn't have to be k is 2, or it doesn't have to be k is 3. And so this should run through all possible values of k, but choosing k to be 2 versus k to be 3 enumerates different situations, right? Because the k equals 2 situation is when you picked 2 things from A, while the k equals 3 situation is when you end up picking 3 things from A and the rest are picked from B. So these are disjoint situations, and the sum rule applies, right? So since, I'll phrase it this way, as my own notes say, since different values of k lead to mutually exclusive situations, here the sum rule applies. By the sum rule, what we need to do is add up over all possible values of k. Right? So this will be a sum k equals 0 all the way up to r of, well, this thingy over here, right? N choose k times m choose r minus k. Okay, so that's the right side. If I again zoom out for a moment, sorry, these, yeah, that's the right side of what's over here. Again, why do we stop the sum at r? It's or why was this first pick a k going all the way up to r? It's because we're only picking r things in total. The counting question is how many subsets of cardinality are there. So let's pause for a moment, see how we're doing, especially with the second way of answering the counting question is kind of usually the thing that gets people. But you see how there's first of all, the product rule, because both things occur here, binomial coefficient because we're talking about combinations, and then once that expression is obtained, then to that product the sum rule applies, because the subsets of A union B that have k equals 2 elements from A, and the subsets of A union B that have k equals 7 elements from A, those are different. So yeah, there's a lot of sum rule, product rule, binomial coefficients, lots of things happening here. No questions. This is bizarre. Really. I'm going to do one other thing. We have just proved this. And I know that our focus here is on combinatorial proof, but I just want to mention, now that we have this thing proved, as a corollary just means something that's true without much extra work. So if n greater than or equals 0 integer, so I have a non-negative integer, then 2n choose n is equal to the sum k equals 0 to n of n choose k quantities squared. So to prove this little mini theorem called a corollary, all you actually do is you just pick n to be equal to r to be equal to m. Right? So if you do that, first of all, the left side, I think, let's just, if n, m, r, like in the theorem we just proved, they were all allowed to be different, but if you just set them all to be equal, then n plus n simplifies to 2n, and r is also n, okay? And on the other side, well, there's an n choose k already, but why is this squared? The thing to recall, actually, so all of these are also, so not all of these, sorry, the k is still k, but the thing to note, if this is an n and that is an n, just the thing to note, so this, and just recall this thing we already said, that n choose n minus k is actually the same as n choose k. So we saw sort of incantations of this already, is that when you have a binomial coefficient and this lower number, I don't want to call it a denominator, if you switch that with n minus k, you end up with the value of that binomial coefficient is going to be the same. So I'm going to give you a moment to think about this next one. Theorem k equals 1 to n of k times n choose k equals n times 2 to the n minus 1. And I want to just give you a hint in starting this. So I want you to come up in, of course, two ways, the number of ways of selecting. Think about, how can you select a committee? And then select a person on the committee to be the chair, to be chair of the committee. So I have not said a lot. I want you to just take the next 3 minutes, just like, what does k represent? What does n represent? Take a moment and give it a try. These are challenging, but I just want you to. Okay, I'm gonna expand the hint a little bit and just say this, right? So let's just say you have like there's n people total, n people, and they're not all on the committee, n people willing to be on the committee, let's say. And then the whole point is on the left side, the idea, and I want you to think about it. I can't do the details right now, right? But the idea of the left side is the size of the committee is k. And so why the sum k equals 1 to n is, well, either the size of the committee is k is 3 or the size of the committee is k is 4. But those are separate situations. It's not, you don't get both. So it's one or the other. It's a size 3, size 4, or size 5 or whatever. So that's why there's this. And then, so n choose k then should be out of the n people who are willing, create the committee. And then out of that committee that has k people, the times k is meant to represent of those k people choosing one person to be chair, right? Choosing the chair. If you prefer, instead of just having the k, you could write k as k choose one. So out of k people total choosing one, how many ways to do that? There's k ways to do this. The right side is rather different. It's the right side is so I'll just write this down here so I don't have to point all the way up there. The n first. Huh? Okay, so this is out of all n people willing to be on the committee, just choose the chair first. Choose the chair first. And then 2 to the n minus 1. When I see 2 to the power, I'm always thinking about power set, right? I'm thinking about all the subsets. So this is of the after the chair is chosen, let's not include that person anymore. Of the remaining n minus 1 people. This is now talking about the number of subsets of size n minus 1, right? So this fills the rest of the committee. Fill the rest of the committee with non-chairs. I mean, this should be spelled out in a bit more detail, clearly, right? But I wanted to just give you some ideas to brew and think about. All right, and just as a reminder, please turn in the take-home exam by the end of the day today in Gradescope. And there will be an online quiz tomorrow.